After you define your residual block class, you've been given another helper function below. This function, dconv, creates a transpose convolutional layer and an optional batch norm layer. Now, with this helper function, the conv helper function from before, and the residual block class, you're ready to define a complete generator class. Let's look back at our diagram. Before, I mentioned that these generators have an encoder portion, a series of ResNet blocks, and a decoder portion, and this is the general architecture. This network, much like our discriminator, will see a 128 by 128 by 3 image as input. This image is going to be compressed into a smaller representation as it goes through 3 convolutional layers and reaches a series of residual blocks. It goes through typically 6 or more of these residual blocks, and then it goes through 3 transpose convolutional layers on the other side. These are responsible for upsampling the output of the ResNet blocks. This is sort of undoing the downsampling that happens in the encoder portion. And the final transpose convolutional layer should output a new generated image of the same size as the input, 128 by 128 by 3. And 3 is just the suggested number of convolutional and transpose convolutional layers here. It's what I'll be using, but you can actually change the number of layers if you want to. Note that most of the convolutional and transpose convolutional layers have batch norm and ReLU functions applied to their outputs. This is based on the architecture outlined in the CycleGAN paper. And it's true for all but the final transpose convolutional layer, which has a tan-H activation function applied to the output. Also, just to complete this description, we know that the residual blocks are made of convolutional and batch normalization layers with a ReLU in between these convolutional layers, so that's why there's no additional activation functions here. Okay, so learning about residual blocks and the complete architecture of a CycleGAN generator, your tasks are to complete the residual block class and then complete the generator class. The CycleGenerator class takes in 2 arguments, convdim and nResBlocks. The convdim is set to a default of 64 for the depth of the first convolutional layer in the generator. This depth should increase in the encoder portion of the network. Then it takes in a number of ResNet blocks, which is set to a default of 6. This should be the number of ResNet blocks in between the encoder and decoder portion of the generator. These ResNet blocks really allow the generator to learn a transformation from one image domain to another, so I wouldn't skip this step. I'd also suggest that you take advantage of PyTorch's sequential wrapper to create a series of 6 or however many blocks you want. I've also left some comments here. I suggest you break up the model definition into 3 main parts: the encoder, the ResNet blocks, and the decoder portion. So define all the layers you need in init, and then define the feedforward behavior as well. As before, I'd say consult the diagram or the original paper if you're confused as to how many layers to make, which layers need normalization, or what kind of depth to use. If you're comfortable with this code, I'd suggest you move on to the next couple of cells and instantiate the necessary discriminators and generators. If you get stuck or want to consult a solution, you can check out the next video.